My name is Xuan Feng. I'm from University of Chinese Academic Science. Today, my presentation is about acquisitional rule-based engine for discovering Internet of Things. Here is my outline. First, we will show our work background. Then it's our proposed rule manner for automatically rule generation called ARE. Following is the design and implementation. Next, we evaluate our performance in the real-world dataset, and to further demonstrate the effectiveness of ARE, we present 3 ARE-based applications. Finally, we conclude our work. Nowadays, many IoT devices with communication capability have been connected to the Internet, such as camera, router, also some industrial control systems and medical equipment. Gartner reported that there are nearly 5.5 million IoT devices were getting connected to the Internet every day, and moving forward 20 billion by 2020. Undoubtedly, this IoT device will promote our economic growth and improve our daily life. However, this IoT device also has some security challenges, such as device vulnerabilities, mismanagement, misconfiguration. The well-known security instance is the Maria-botnet, which compromised and exploits many IoT devices as a botnet and performs DDoS attack, crossing the internet service disruption across United States and Europe. It is also reported that some IoT devices, such as surveillance device, is used to mine Bitcoin. Today, there is two basic approaches to addressing these security challenges. The first one is reactive defense. It needs to download the film and do some offline analysis. Another way is the proactive provision, which can prevent the potential damages by protecting malicious source, which is more efficient to defend against these large-scale security incidents like Maria-botnet. To protect this IoT device in a proactive manner, discovering, cataloging, and annotating this IoT device is a prerequisite step. Device annotation always contains the IoT device type, come from a vendor, and with the product model. The number of device annotation is very large. It cannot be labeled by manual effort. And traditional fingerprinting-based way cannot be used in the IoT device for the high demand of training data set and a large number of device models. Also, the traditional binary grabbing way, such as NMAP and ZTAG, they use regular expressions and keywords to label this IoT device. The rule generation is in a manual fashion, also needs some technical knowledge, and it is impossible for larger scale annotations, and it is also hard to keep updated. However, in this paper, we aim to automatically discover and annotate this IoT device while mitigating the cost in terms of human effort and training data set. Our key observation is based on that manufacturers always hard-code some device information, like some keywords, into their application layer data to distinguish this device. Like the right picture is the HTTP application layer data of an IoT device, which may contain some keywords. And there is also some web pages to describe this IoT device, such as product review or something from Wikipedia. Given an application layer data, we can search these keywords into search engine like Google. And then we can identify from the search result that this keyword is a TP-Link wireless router, and this keyword is a device model. In this way, we can label an IoT device. Our way is rule-based, and the automatic generation is mainly based on the relationship of application layer data of IoT device and the related description web pages. Although the basic idea is very simple, there are two major challenges. The first is the application layer data is hard-coded by its manufacturer, and there is also larger number of device notations. Notably, manufacturer would release new product and abandon outdated product. Manually label every description web pages is impossible. To address these challenges, we propose an Acquisitional rule-based engine called ARE. ARE can automatically generate rules for discovering IoT device in the cyberspace. The core part of ARE is the rule manner. As shown in the right picture, ARE uses a transaction dataset to man rules, and the transaction dataset is a relationship between the application layer data and its device description in the internet. And ARE uses device entity recognition to extract the device information, and finally use the actual algorithm to learn rules from the transaction data. We define the transaction data as a pair of textual units consisting of application layer data of IoT device and the related description web pages of IoT device. And a rule is the association between a few features extracted from IoT device and the device annotation extracted from the web pages. Traditional name entity recognition is high domain specific, and is not designed for IoT domain. Will achieve poor performance in IoT domain. So we proposed a device entity recognition called DER. DER is a combination of corpus-based and rule-based. The corpus is used to extract device type and vendor name, and the rule-based is used the regular expression to extract the product name. As shown in the red table, there is about 20 device types and more than 1,000 vendor names we use in DER. However, this heuristic method have a poor performance due to high false positive in terms of the device type and the product name. To address this problem, we use a local dependence between these entities. As shown in the red table, the true IoT device always have a strong dependence upon one another. The vendor entity first appears, followed by the device type entity, and finally the product entity. Or the vendor entity first appears, or the product entity appears, and the device type entity follows. In this way, we can achieve a high performance to extract device annotation from this description web pages. Then the Ruminer uses the actual algorithm to establish the relationship between extract keywords from the response date and the device annotation extract from the web pages in the transaction date. The actual algorithm has two parameters, and the first is support. It's used to indicate the frequency of the A appears, and the confidence is the frequency of the rule under the context in which the A appears. We can say when the support is very low and the confidence is about 50%, the actual algorithm works well. After the rule generation, we can establish the relationship between these extract keywords and the device annotations. As shown in the red table, it's a few example rules we learned from ARE. And the red part is some keywords, and the red part is the device annotation. Here is the design and the implementation. ARE consists of 4 parts: the transaction collection, rule miner, rule library, and the planner. The transaction collection is used to collect the response date from remote device and extract some keywords from the response date. Then search these keywords in the search engine to collect more description web pages. The rule miner is the core part of ARE we have explained before, and the rule library is used to store these rules, and the planner is used to update the library. Following is the real-world performance evaluation. We use 2 datasets to evaluate the ARE. The first dataset, we randomly choose more than 300 IoT devices and across 4 different device types and 60 different vendors and more than 300 different products. And the second dataset consists of 6.9 million IoT devices that our application collects on the internet. We randomly sample 1,000 devices across 10 device types and 70 vendors. Totally, ARE can generate 100,000 rules in 1 week, and more than 90% of rules with a fine-grained annotation containing device type, vendor, and product. Compared to Nmap, there is only 30% of rule with a fine-grained annotation. As shown in the red tables, ARE can achieve high performance and coverage above 95%. We also use ARE and Nmap to tag the same number of response package. We can say ARE can achieve a high coverage than Nmap and find more device annotations. ARE can also dynamically learn the rules, as shown in the red picture, with the increase of network range, and the number of rules is increasing as ARE learn the new rules. All this experiment is conducted on a desktop PC, and the time cost of ARE is very low in practice, and the main cost is the internet cost. To further demonstrate the effectiveness of ARE, we conduct 3 ARE-based applications. The first is the internet device measurement. We collect 3 application layer data from sensors, and we also deployed the collection module on Amazon and to collect the RTSP application layer data. Using ARE, we can find 6.9 million IoT devices, and there is a large number of IoT devices exposed on the internet, and there is also a long tail description of this IoT device. And we can say the United States have the most IoT device, and the next is China, and the following is Brazil. IoT device, ARE also can be used to detect some compromised IoT device. We deployed some honeypot for monitoring the traffic on the internet. We use ARE to label this captured IP address. A normal IoT device should never access our honeypot. If an IoT device accesses our honeypot, it is because that have been compromised or misconfiguration. Our honeypot is across from 4 countries, 7 cities, and the duration is about 2 months. We can find about 50 compromised IoT devices every day. In total, we find 2,000 compromised IoT devices, including DVR, router, NAS, and we also find some smart TV box, except the malicious behaviors. ARE also can used to find the underlying vulnerable device by cross-match the exposed IoT device with the vulnerability information library. And we can say that there is also a large number of underlying vulnerable devices in the cyberspace. And the most vulnerability is about the improved implementation, about such as credential management and the improved access control. This fall is very easy to be avoided if the developer to pay more attention to the security. Finally, we conclude our work. We propose the framework of ARE, and it can automatically generate rules for discovering IoT device without human effort and training dataset. We also implemented a protocol of ARE and evaluate its effectiveness. ARE can generate a larger number of rules in 1 week and achieve more fine-grained rules than existing tools. We also apply 3 ARE-based applications, and we can find larger number of IoT devices exposed on the internet, and some device is underlying vulnerable. We also can find thousands of compromised IoT devices. Thank you.
Hi, Matt Bernhardt, University of Michigan. I just wanted to say this is a great talk. I was wondering, have you thought about, you said you built a web crawler for this. Have you thought about hooking it up with census? I know you use census data, but is the rule set going to be available publicly? Because it's definitely something that I think could be rolled into census. It would make it a lot easier for us. So you generated this big rule set. Is that publicly available, or is the system available somewhere? Have you, are you going to open source it? Yeah, okay, great, thanks.
I have a question. So you had a list of the devices, kinds of devices. How easily can that list be expanded as the number of IoT devices proliferates and new types of devices are introduced?
We cannot find the new. We cannot find the new kind of IoT device, but we can find the new model. As shown in the.
New models of all things.
Yeah. As shown in the table, we define some device type and the vendor, but the main work is to find more device models, because the device type and the vendor we can manually label them just a little human effort from Wikipedia or a small data site.